Okay, so thanks, Sonny, for giving us a very well-rounded background information about Mars. And you already went through most of my background slides, but we're going to go through them again. So welcome to Mars. I'm going to talk about my project on probing Mars northern plain stratigraphy with impact craters. So my name is Lu Pan. I'm from California Institute of Technology. And right here, you're looking at a visible image of a kind of stretched image of Mars. And the northern plains are these darker regions. This is Acidalia, basically. And this is where we're going to look at today. So one of the striking features about Mars when you look at this topography is the hemispheric dichotomy. And the southern highland is the average elevation of the southern highlands is about 5 kilometers higher than the northern lowlands. And you can see it's also very heavily cratered because it has which lead to our understanding of the southern highlands being very ancient in age. They're not just different on the surface, they also have an intrinsically different crustal thickness. The northern plains are much thinner, have a much thinner crust than the southern highlands. But what's more interesting about Mars is that in the recent decades, there are thousands of outcrops of hydrating minerals detected on the surface of Mars, including iron magnesium phyllosilicates, hydrated silica, chlorides, carbonates, and sulfates. But you can see most of the hydrating minerals are concentrated in the southern highland area, and only a few spots are detected in the northern plains. And this also leads to a new understanding of the chronology of Mars. So we have divided from crater counts and understanding of major events in Martian history. People have divided Martian history into 3 main epochs. So the oldest being the Noachian, and then Hesperian and Amazonian age. And from the mineralogy side, we find that most clay minerals people find are related to the oldest terrains. So people believe that these clay minerals represent early warm and wet Mars climates that transitioned into a more acidic atmosphere with a lot of volcanism period in the Hesperian, where the sulfate mineralogy dominates the surface. And when you move to the Amazonian, you don't see a lot of hydrating minerals. They are mostly anhydrous ferric oxides that are correspondent to the Martian surface we see today. But today, I'm going to mainly talk about the northern plains of Mars. If you have read the book Martian, they landed here in Acidalia, where I'm going to talk about. So we don't know very much about the northern plains. We don't have such thousands of outcrops of hydrated minerals. And what we know about the northern plains is like this. So from the Noachian age, we know there is a heavily cratered basement in the northern plains. This is inferred from the quasi-circular depressions, or they call it ghost craters, that people found using the topography data. And this is an important discovery because this tells us that the dichotomy between the southern highlands and northern plains are set very early on in Martian history. And the northern plains has a very different surface environment because there are later sediments and lava flows deposited into the northern plains. And a major question about the northern plains is that people suggested there could have been a global ocean that existed somewhere in late Noachian or early Hesperian. And this has been argued back and forth, but we still do not have definite evidence for such an ocean to exist. When we move to the Amazonian age, there are not so much going on in the northern plains, except for the polar deposits due to the radical obliquity changes of Mars. And also, there are some surface geologic features like this one. So these little conical features are hypothesized to be a mud volcano that involves some volatile activities. So today, our project is to use CRISM data to look at the northern plains and try to see if we can understand these important questions whether there has been a sustained global ocean in the northern plains. Has there been recent groundwater or ground ice activities, and more generally, what is the stratigraphy of the northern plains itself? So by CRISM, I mean the compact reconnaissance imaging spectrometer for Mars. So this is a visible near-infrared spectrometer on board Mars Reconnaissance Orbiter, and it has been orbiting Mars for more than a decade, I think. And we obtain information like this from CRISM. So x-axis is wavelength, and y-axis is reflectance. And from the different spectra of the surface in the visible near-infrared wavelength range, we can get electronic transitions like this from the mafic minerals, and also vibrational transition bands that are sharper and more in the longer wavelengths. And these represent water-formed minerals like smectites or hydrated silica. Or we can get these continuum slopes that represent an alteration rind or coating. So what we are going to do is to specifically look at the impact craters in the northern plains. Because the northern plains, as I said, we don't have too much exposure of hydrated minerals because it's mostly covered and there is some alteration on the surface. So we don't detect, it's very hard to detect those hydrated minerals in the northern plains. That's why we're going to the impact craters. You can see from in the panel A through C, impact craters of different sizes can penetrate through different layers in the stratigraphy and expose all this mineralogy on the surface. You can see the deepest layer exposed in the central peak and in the proximity, in the distal area of the ejecta blanket. There is one complicating factor about hydrated minerals is that these could have formed after the impact when there is a hydrothermal, when there are impact-induced hydrothermal activities formed because of the impact. These have been proposed for Mars, and possibly they did exist for Mars in certain ages when there's liquid water around. So we have to look out for such hydrated minerals in post-crater formation hydrothermal activities. So that's the main idea. Here I'm showing the map of the detections of mafic minerals and hydrated minerals in large craters. So all of the white dots are craters larger than 30 kilometers, and these are, but most of these do not have CRISM coverage. So within Acidalia Planitia, we have surveyed all of the craters with CRISM coverages, and found some of them have both mafic and hydrated minerals. There are previous works that looked at this area and found mafic minerals in small craters in Acidalia and hydrated minerals in 9 of the large craters within the northern plains. But today, we're going to show you a complete survey of these northern plains data set and integrate both mafic and hydrated signatures and try to understand their relative stratigraphic relationship and place some loose constraints on what the stratigraphy looks like. So these are some preliminary results from Acidalia Planitia. 61 CRISM targeted images have been studied, and 44 are detected with mafic minerals and 25 with hydrated mineral detections. So on this map, all of the stars represent craters larger than 30 kilometers, and all of the dots represent smaller ones. So there are even smaller craters that are not shown on this map. You can see there is a general trend that the larger craters show more of a hydrated minerals. So here I have divided into iron magnesium phyllosilicates and other hydrated phases, because to identify iron magnesium phyllosilicates, you need to find the 2.3 micron absorption, which are generally very weak in the northern plains. So sometimes you do not see them. And another observation from this survey is that craters near these outflow channels generally have very weak detections. So sometimes it's very hard to pinpoint there is a hydrated detection there. And I have some examples of how we detect these minerals. So this is, on the left, I'm showing the CMIS image of Bonestell Crater and Davis Crater. And these shapes on the image are the CRISM footprints with the little dots showing what kind of mineral detections there is. On the right, I'm showing the spectra of different minerals. This panel is the hydrated mineral with the 1.9 water band and the 2.3 metal OH bands. These, like in Davis Crater, it's very weak, but it's right above detection threshold. In Bonestell Crater, it's more clear, and you can see there's a 2.35 absorption feature, which is a closer match to chlorite instead of the non-tranite and sapnite samples. And on the right panel, these broad absorptions represent iron in the mineral. So these are olivine spectra and pyroxene spectra. What is cool about Davis Crater, though, is that you did not only see these hydrated minerals in the central peak, you also see them on the crater walls and the crater ejecta, which is consistent with all the crater excavation models. So as I said earlier, we need to distinguish whether these hydrated minerals formed pre or after impact. Oh, I'm running out of time, okay. So here are just some beautiful images showing where these detections are made, and you can see them on the rocky ridges where meter-sized boulders have been falling off these ridges. And the same one here, we have a layered mega block. So this is a huge block in the central peak that is definitely uplifted from depths. So assuming we know that these minerals are excavated from depths, we can calculate a maximum excavation depth from the size of these craters. So in this figure, the x-axis is the crater rim-to-rim diameter, and the y-axis is the maximum excavation depth. And I'm showing in each, like these three lines are different models for crater scaling, basically. And you can see only craters larger than 20 kilometers are found with hydrated signals. And these craters generally excavate depths from deeper than 1.5 kilometers. So here's the summary. And in the future, we're going to complete a survey outside of Acidalia and build a complete database and place upper and lower bounds of the thicknesses of different layers. And we hope to use these impact craters, we can decipher the changing acreage history of Mars and better assess the habitability and the habitability of early Mars and how it changed through time. And that's all. Thank you.
So do we have any questions for Lou?
So I'm just wondering, in the smaller craters, you're saying that basically you don't see these hydrated minerals, right? Yeah. When you say hydrated minerals, do you just mean an OH group, or do you mean basically minerals that have been altered by some sort of long-standing water body, like a clay or something?
So in here, when I say hydrated minerals, I refer to the specific spectral class with H2O band. So I think this represents a mineral with H2O in the mineral structure. So it can be a clay mineral, but it can be other like amorphous silica or things like that have the H2O. So it's a more broader range of minerals.
Okay, because in the case of Gale Crater, I understood that there was actually like alteration type minerals. I mean.
Yeah. Yeah.
So what I was curious about is whether these larger craters could potentially be larger water bodies and hold, not evaporate quite so quickly, basically, and be able to alter minerals over a longer standing period in such a, thin atmosphere where things would evaporate rather quickly. Yeah. So that was all I was curious about. Thank you.
Yeah. That's definitely a possibility, and that's why we're searching for like definite evidence for phyllosilicates and other clay minerals. And from that, you can infer how much water there is involved, right?
All right, let's thank Lou one more time.